we are going to look at two things, mean value theorem and Rolle's theorem. We'll probably kind of divide it up and do one each day. These are not especially difficult, but they do have some requirements to use them, so you do have to pay close attention to those things as we move forward. So today, let's start with Rolle's theorem. Rolle's theorem tells us if you have a function with these three requirements, so it has to be continuous on the closed interval. Continuous we know means there's no breaks in our graph, right? And it has to be differentiable on the open interval. That means the derivative has to exist everywhere except maybe at the endpoints. And the endpoints are equal. Right, so if you think you're drawing a graph, there's no breaks in it, it's continuous, and it's differentiable, so no like asymptotes, no sharp corners, the derivative exists, it's a nice smooth curve. If the ends are equal, then the only way you could start and stop at the same point is if somewhere you have a horizontal tangent line. So somewhere in between, there has to be a point where the derivative is 0. Right? And the next picture, I just gave you some scenarios of this. It could be that you just have a horizontal line, starts and stops at the same point, and then any point on this line would have a derivative of 0. You know, you might have a maximum in there. You could have a minimum in there. You could have multiple maximums or minimums. But ultimately, if you don't have any breaks in it, then if you start and stop at the same point, you have to have somewhere where the derivative was 0. Do you guys, I love space to prove this for you if you want. Do you want the mathematical proof behind it? Are you interested in that?
Sure, let's see why, just in case we need it.
Yes, otherwise no.
You don't really have to have it, but if you're, you might need to. So you want,
I think we should just watch it happen.
watch it happen. Okay, so you essentially have to take into consideration every possibility if you're going to do a proof. So case 1 is when our function is constant. That's the horizontal line. Okay, it never changes. So if that is the case, then what is the derivative of a constant? 0. So every point in the interval a to b satisfies the theorem. Because the derivative is always 0, so any point I pick makes the derivative equal 0. Fair enough? Second case. So let's say that my function, f of x, is greater than the endpoint at a for some value in the interval a to b. Okay, so a is my starting point, and I'm saying if it's not always constant, then maybe somewhere it's higher than it started. Okay. So by the extreme value theorem, that we saw last week, if you start somewhere and then you go above, and we know we have to come back down because a and b have to be equal, there must be a maximum in the interval a to b. And if there is a maximum, let's say point C, what's the derivative anywhere that there is a maximum? 0. So it meets the requirement. So if somewhere the point is higher than it started and it comes back down, we have to have a maximum, and we know that if there's a maximum, the derivative is 0. Case 3 would be when your function is lower than the starting point at some point, and that would be the same as case 2. So you would work it out by the extreme value theorem. That means there's a minimum between A and B, and we know if there's a minimum, the derivative is 0. So it works. So that's just kind of a rough idea of what a mathematical proof might look like. We took into the 3 possible cases. It's always the same. It went up somewhere, it went down somewhere. No matter what, the derivative has to be 0. So if the position of a moving object at 2 different points, or 2 different times is equal, what does Rolle's theorem tell us? All right, so I have an object that's moving, and if it hits the same position twice, what does that mean? So if it starts somewhere, and then it comes back and it hits that point again, what's happening somewhere in the interval?
There's a maximum.
There's a maximum. So think about, that means the derivative is 0, right? The derivative of position is
Velocity.
velocity. So it's saying at some point the velocity is 0. Which doesn't that make sense? If I take a ball and I drop it, it's starting out with a negative velocity. It's going to hit the ground and bounce back up and have a positive velocity. What happened at the instant when it was on the ground?
0.
The velocity was 0. It quit moving for a second. So all it's saying is at some point in the interval, the derivative was 0. So the velocity was 0, which makes sense to us. All right, so let's look at how we would apply it to our scenario. So we are going to be looking at equations most of the time. So here's an equation and an interval. I want to find a number C that satisfies the conclusion of Rolle's theorem. Anytime I ask you to do Rolle's and mean value theorem, I'm going to tell you that you have to check the conditions first. So my criteria. What has to be true in order to use Rolle's theorem? First thing, it had to be continuous on the closed interval, and it had to be differentiable on the open interval. All right. So this is like saying a square root of x minus the square root of x cubed. When is this not defined? When can you not do a square root? Negative numbers. If I'm between 0 and 1, do I have any negatives? No. All right. So my first criteria, f of x is continuous on 0 to 1. I am not going to require you to show me a lot of work to justify that. I want you to state it so I know that you're thinking about it, but I'm not going to make you write out a huge long explanation. Second thing, it has to be differentiable. So let's find that derivative and make sure it works. So the derivative of this function would be what? I'm going to come down kind of below for a minute. So this is like saying 1 over 2 square root of x minus 3 square root of x over 2. Do we agree with that? When is this not defined? We all agree. At 0, this derivative doesn't exist because you would be dividing by 0, right? But look at your criteria. Your criteria says it has to be differentiable on the open interval, 0 to 1. So it's okay if it doesn't exist at 0, but it has to exist everywhere between 0 and this would. So again, you don't have to show me a lot of work. We're going to do the derivative eventually, so I like to do my derivative first and look at that. Now, what if my interval had been -1 to 1? Would we be able to use Rolle's theorem? No, because first of all, it wouldn't have been continuous the whole time. I couldn't have worked with the negatives. Second of all, it wouldn't have been differentiable everywhere, because 0 would have been included in that interval. Okay, what's...
Isn't 0 included because it's a closed, or it's a...
Yes, so it is included, but the criteria, the differentiable, is the open one. All right, third criteria, the endpoints have to be equal. So let's check if that is true. All right, if you plug in 0, we get the square root of 0 minus the square root of 0 cubed, which is 0. If we plug in a 1, we get the square root of 1 minus the square root of 1 cubed, which is 0. And those endpoints are equal. So my criteria is all met. It's continuous on the closed interval, differentiable on the open, the endpoints are equal. Then what does Rolle's theorem tell us? There is some number in my interval where the derivative equals 0. So either a maximum or a minimum. Alright, so now let's find the number. We know there's something between 0 and 1 that would make this equal 0. We already did the derivative. So if I set that equal to 0, so if I cross multiply, that would be 6. What's the square root of x times the square root of x? X equals 2, so x is 1/3. Is that between 0 and 1, like we said? Yeah. So my direction was to find the number c that satisfies it. My number is 1/3. It's possible that I might have gotten multiple answers. If so, you would only include the ones on your particular interval. So if I had worked this out and I got 1/3 and 5, I wouldn't use the 5 because it wasn't in the interval I originally asked you about. So 1/3 would have been my answer. Let's do another one. Here's a function. Does this satisfy Rolle's theorem? So let's check our criteria. It has to be continuous. Okay, this is just another way of saying 1 minus the cube root of x squared. Can you do the cube root of even, or of both positives and negatives? Yeah, we can do the cube root of anything. So my first criteria, it is continuous on the interval -1 to 1. I don't have to worry. Cube root is like the sideways chair, so it always works. Let's see if it's differentiable. So if I do my derivative, what do we get? So that's the same thing as saying -2 over 3 times the cube root of x. This has to be differentiable, so the derivative has to exist everywhere between -1 and 1. Does this derivative exist everywhere? Where does it not? This is not differentiable at x equals 0. Since 0 is in the interval -1 to 1, we cannot use Rolle's theorem. Now, if my interval had been 1 to 2, would we have been good? Yeah, because from 1 to 2, the interval would exist. The derivative would exist. but we could not do it at 0. All right. Most of the time, I'm going to be giving you like polynomials and things. I say most of the time, not always, but a lot of the times when we use this. With polynomials, we already know that a polynomial is always a nice, smooth, continuous curve, and the derivative of a polynomial always exists, right? So if it's a polynomial, I am okay with you just stating it's a polynomial, so it's continuous and differentiable. If you catch it and you just want to state that, that's fine, because those are results that we have already had. So my criteria, you just want to say polynomial, so continuous and differentiable. You can kind of combine steps 1 and 2. You're welcome to still do them separately, but polynomials are an automatic guarantee, so that's really criteria 1 and 2. Criteria 3, what do we have to check? The third requirement for roles is the endpoints have to be equal. So if we plug in a -2, -2 to the third is -8. -2 squared is 4. Minus 4 times -2 minus 2. So we get -12 plus 8 minus 2. So we get -6. And if we plug in a positive 2, we get 8 minus 4. And we also get -6. So those endpoints are equal. So we can do Rolle's theorem. So Rolle's theorem says that the derivative equals 0 somewhere between -2 and 2. So my derivative is 3x squared minus 2x minus 4. Set that equal to 0. If we try box method, I don't think it's going to work. Let's see. Anything multiplied to -12 and add to -2. No. So if box method doesn't work, how do we solve it? Yeah, quadratic formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's 4 plus 48. 52. We have to break down 52. Let's see, that's 4 and 13. Square root of 4 is 2. Divide everything, so we get 1 plus or minus the square root of 13 over 3. That may be a little harder for you to verify. It should fall between -2 and 2. If we wanted to check, we could use our calculator here and verify 1 plus the square root of 13 divided by 3 is 1.535. When you do the minus, it's -0.8685. So both of those do fall between -2 and 2. So this time we got 2 values in our interval that worked. So your choice. That's Rolle's theorem. We have the mean value theorem left. Do you want me to just stop here today let you do Rolle's theorem practice and then tomorrow do mean value theorem? Okay. So I have a handout. The Rolle's theorem problems are actually the back. So you're ready for questions 7 through 12. The front is mean value theorem. Sorry, not the real. So we're doing questions 7 through 12 for tomorrow. The first one, 7 and 8, says determine if it can be applied. So you have to check your criteria. These are the less nice ones, so you need to actually do your derivative and make sure it exists there. Questions 9 through 12, it should work for all of those, but I want you to go ahead and verify your criteria. Now, all of those are polynomials, so if you want to just say it's a polynomial, so it's continuous and differentiable, that's okay.
What does this continuous mean? I don't understand.
Okay.
One of these. Yeah, I can wait.
No, you're good. So